Today we're going to be learning about a new type of function called an exponential function. So the equation for the exponential function is f of x equals a times b to the power of x. Just like with quadratic and linear functions, the x is going to be the input of the function, and the f of x, which we know means the same thing as y, is going to be the output of the function. The A, I know that these arrows are kind of weird, but this is pointing at the A, and this is going to be the initial value, so however much there is at the beginning. And then this B value is going to be the growth or decay factor. So there are two types of exponential functions. Growth functions, they look like this, where they are going up, the arrow kind of goes up. Then decay is whenever we have something that is shrinking. You can see here at this table, if you remember, anything to the power of 0 is 1. So this is basically a times 1, which we know equals a. Then here we have the power of 1, right, which is just ab. Okay, and then each time that we have it, it's going to get multiplied by another b. So here we would have 4 b's that would get multiplied, and we would end up with ab to the 4th. And then on the last one, we would have 5 different bees. And you can see that this grows very quickly, that when we multiply it by another bee each time, that it's going to grow or shrink very quickly. Okay, we can tell if it's going to be a growth function if the b value is greater than 1. So for example, if the b value is 2, if it's 4, any numbers that are bigger than 1, it's going to be growth. If it's in between 0 and 1, so for example, if it's 0.5 or 0.7, those are going to be decay functions, okay? So here you can see the b value is always the number that's being raised to the x power, okay? So here you can see that a is 1/2 and that b is 1.5, which makes this a growth function because the b value is bigger than 1, okay? Example 2, we know that a is 2, b is 0.5, so that's going to be a decay function since 0.5 is in between 0 and 1. Here you can see these look a little different. They don't have the parentheses, and that's because the a value is 1. Anytime you don't have parentheses, that means you have an a value of 1. Now our b value is 2, so this is going to be growth. Here you can see a is 1, our b is 0.8, so this is going to be decay. Okay. If we're going to have some examples, okay, in this first table, our a is 1. Remember, if we don't have the parentheses, our a value is 1, and our b value is 2. Okay, so the a value is the y-intercept. It's always going to be across from the 0 in the table. So we can see here, we're going to have 1. We can go ahead and make a point right here at 1 because we know that that's going to cross through there. And then here for our y-intercept, we have 0, 1 for our first equation. The b value being 2, that means that's what we are multiplying by every single time. Okay, so in order to get to the next box, we would do 1 times 2. Okay, so that would give us 2. Then we would do 2 times 2. That would give us 4. Then we would do 4 times 2. That would give us 8. Okay, now to go the other direction, we kind of have to think in reverse, right? What would we have multiplied times 2 to get 1? Well, the answer is 1/2, okay, or 0.5. And then before that would have been 1/4 or 0.25, okay? So either one of those is completely fine. And when we go ahead and put that on the graph, we just want to make sure that we graph these appropriately. You can see it curves up here. It's going to get closer and closer to 0. Now, it's important for us to note that these graphs are going to get closer and closer to 0, but they're never going to actually cross 0. And the reason is because there is no limit to how small these numbers can get before they get to 0, right? Like if you think about what would come before 1/4, right? We had 1/4. If we cut that in half, we would be 1/8. If we cut that in half, it would be 1/16, 1/32. Okay, so we can just keep getting smaller and smaller and smaller and smaller and never get to 0. Okay, now we're going to, so that is called an asymptote. So the asymptote means what line is this graph getting closer and closer and closer to without actually touching it, right? And the answer to that is going to be y equals 0 since it's a horizontal line, okay? Our domain, you think about Dr. XY, loves biology, okay? Remember, the domain is left to right, and this graph is going to go left forever and right forever. So we say that all real numbers, okay? The range is going to be all the numbers above 1. We want to make sure we don't include that line underneath our greater than sign because it never actually touches 1, okay? If we were to go through and do a decay function, okay, it would be similar. We would say here, let's do this one. A is 2, B is 0.5. Okay, so here we will go ahead and put our 2 right across again from the 0. We can go ahead and make it on here, and then also here 0, 2. Okay, and then here we're multiplying by 0.5. So every time it's going to get cut in half. So half of 2 is 1, half of 1 is 0.5, half of 0.5 is 0.25. And then the other direction, well, what would we have cut in half to get to? 4. What would we have cut in half to get 4? 8, okay? So it's kind of the reverse of the previous function that we did. We have negative 2, 8 here, 4, then we have 0.5 or 1, 0.5, and 0.25. So you can see this is the decay function. It is going down, whereas our growth example was going up. But we are going to have very similar answers to all of these other questions. As a matter of fact, anytime that this is not a real world problem, it's just an abstract graph with no labels or situation attached, we're always going to have the same answers to these questions. So we are still going to have an asymptote of y equals 0. We're still going to have a domain of all real numbers, and we're still going to have a range of y is greater than 0. All of these are going to stay constant unless we have a real world problem that has labels attached to it.